Hi and welcome back. Today we're going to be looking at the first of the videos that look at trends so that we can see in the properties of elements in the periodic table. Today we're going to look at physical properties rather than chemical properties, how these arise and what the trends are that we need to know both across a period or down a group. So let's have a look at some of these and get started. So physical properties of the elements that we're going to look at in this video include atomic radius, so the actual radius of the atom itself or the size of the atom, the ionization energy, the electronegativity, and reactivity we'll look in another video. These all exhibit periodicity, that is, that they exhibit that pattern of repeating similar properties that we see as we look at elements as we move through the periodic table. These properties all tend to be dependent on the strength of attraction between the outer shell electrons in the nucleus, which is always dependent on two factors. The first of these factors is what we looked at in our previous video, which is core charge, how strongly the outer valence shell electrons are attracted towards the nucleus, as well as the shell or the distance from the nucleus, because the physical distance from the nucleus that a valence electron is, the more weakly it will be held. If you think about when we pull magnets apart, the further apart that they get, the less of that pull towards each other that we feel. Same goes for the nucleus and the valence electrons. So as the valence electrons get physically further away from the nucleus, that attraction drops off. So this will relate to the number of shells that we see. So if a valence electron is in shell 5 versus shell 3, it will be held less tightly to the nucleus. And then that will also depend on the core charge, whether it's in group 1 or group 7, something like that. So let's start having a look at some of these properties. The first one we're going to have a look at is atomic radius. So this is literally relating to the size or the radius of the sphere that we define as the atom. This decreases as we move across a period, which means that our group 1 elements over here, our alkali earth metals, are going to be larger than our group 17 or noble gases. These ones are going to be much smaller. And then as we go down a group, they also get larger. So it increases as we move down a group and decreases as we move across a period. When we think about this, there are two factors. Across the period, we are increasing our core charge as we move from left to right. So as we move from left to right, core charge will increase. They are in the same shell. Okay, so if we look at period 3, everything is, the valence shells are all in shell 3. So they're the same distance from the nucleus, but we have increasing core charge because as we are adding in one new proton for each step across the periodic table that we have, we're increasing the attraction of the nucleus, but the valence shell electrons are all going into the same shell, so the core is the same, so we have an increase in core charge. You may remember that for sodium, with an atomic number of Z, this was 11 minus the 10 shielding electrons gave us a +1 core charge for sodium, whereas for chlorine we have 17 protons minus 10 shielding electrons gives us a +7 core charge. So we can see the higher core charge means that the electrons will be pulled more closely to the nucleus of the atom, which decreases the size of the electron cloud, making the atom smaller. When we look at the same group, however, these all now have the same core charge, but we're adding an extra shell. And by adding an extra shell, those electrons are more distant from the nucleus. We've added that layer onto the onion. So we've increased the size of the actual atom, as well as them not being able to be held as tightly to the nucleus due to that greater distance. First ionization energy will be a new idea. This is something that we need to be able to define. And this definition is something that you will need to be able to memorize. So you should add it to your list of vocabulary terms that you must know. The first ionization energy is the minimum energy. It's the minimum energy needed to remove the first electron, okay, from the valence shell. This is when the atom is in a gaseous state, its highest energy state. So it's the minimum energy required to remove the most loosely held electron from 1 mole of atoms in the gaseous state. We haven't learned what the mole is yet, but essentially that is a fixed number of atoms. And it can be shown by this equation here. That is, a neutral gaseous atom loses 1 electron, becoming a positive ion. So the amount of energy required to do that, it's an endothermic reaction because the energy is required, we have to put energy in, is another one of the trends that we see. And what we see is that first ionization energy increases again just as we move from left to right. The ionization energy increases, so it becomes harder to remove an electron as we move from left to right across a period. And as we go down a group, the ionization energy decreases. So electrons become easier to remove. If we think back to our core charge, this makes sense because as we move from left to right across the period, the core charge increases, meaning the electrons are more tightly held to the nucleus, so they require more energy to be removed. Conversely, as we move down a group, we are adding shells, so the electrons are further away from the nucleus, are held less tightly, for they have the same core charge, now operating over a greater distance, and those electrons are easier to remove, so they require less energy. So these again rely on the distance of the electron to the nucleus, and the size of the positive or nuclear charge, the number of protons, and the shielding effect, i.e. the core charge. The greater the ionization energy of the atom, the more stable the electron configuration of that atom, which means it makes sense that as we move from left to right across the periodic table, our noble gases are the ones that show the highest ionization energies. So as we move across, getting more and more full shells, the more stable the electron configuration becomes, and the higher the ionization energy. Electronegativity is another term that we need to be able to define, and this cartoon here represents it pretty well. The electronegativity of an atom is its ability to attract bonding pairs of electrons or draw electrons towards itself in a bond. So the IB specifically refers to it as the ability to attract a bonding pair of electrons or a shared pair in a diatomic covalent bond. This is not necessarily how specific we need to get into for VCE. Simply the electron attracting power of an atom is what we need to think about it. So the higher the electronegativity of an atom, the more it is able to attract electrons or draw electrons to it. So this makes sense that non-metals will have a higher electronegativity because they are wanting to gain electrons in order to form stable ions, whereas metals have low electronegativity. They are able to readily give up their electrons to form positive ions. The Pauling scale is the scale that we use to measure electronegativity. This is not something that you have to memorize, and you do not need to know numerical values for the electronegativity. What you do need to know is that fluorine is the most electronegative element, and that, of course, is up here in group 17. So as you can expect, our electronegativity increases as we go across the period from left to right, and it decreases as we go down a group. And this is what we see here. So You can see here we're going to increase across a period and it decreases down a group. So the most electronegative element we see is fluorine. Anything that is lower than fluorine or to the left of fluorine will have a lower electronegativity value. And we can see that here. The noble gases are unable to attract electrons towards themselves because they have stable complete octets, so they are not given an electronegativity value. You can also see that chlorine, oxygen, nitrogen contain high electronegativities and they have a close proximity to fluorine in the periodic table. Of course, our metals are very low in electronegativity. In fact, francium, which is our most reactive metal, i.e. most likely to give up its electron, has the lowest electronegativity. It's the most electropositive element. So electronegativity increases as we move across a period from group 1 through to 18, and it increases up a group, decreasing as we go down the group. Again, this can be related to the distance of the electrons from the nucleus and the core charge. Just a note on ionic size versus atomic radius. Atomic radius refers to the size of neutral atoms, whereas the ionic radius is referring to the size of the ions that are formed. Because metals lose electrons and form cations, the cations will always be smaller than the neutral atom. If we consider sodium, again with its 11 protons and 11 electrons in the neutral atom, when we form Na+, we remove this one electron. That actually reduces that entire third shell away. So we can see now that the radius of the ion is smaller, as well as our core charge will now be 11 minus 2, which is plus 9. So these new valence shell electrons, or the outermost electrons of the ion, are pulled much more closely to the nucleus due to the strong attractive force of that increased core charge. On the other hand, when we look at non-metals, such as chlorine, which is 17, now when we add in the electron to form the chlorine minus or chloride ion, it goes in here, remembering that like charges repel. So as I add in an extra electron into that shell, those electrons will repel a little bit, causing the size of the ion to swell, to get larger. This means that it's going to increase its overall size. Also, it's important to remember that even though we added in an electron, we haven't changed the number of protons and our core charge won't have changed. So the core charge stays the same, 17 minus 10 at plus 7, but now instead of being plus 7 applied across 7 electrons in the valence shell, it's now plus 7 applied across 8 electrons in the valence shell. So those electrons are not held as tightly to the nucleus, and they are going to repel each other a little bit more. So overall, for negative ions, we see the radius of the ion being larger than that of the neutral atom. So it's important to be able to recognize these trends and be able to explain them in terms of core charge and the distance from the nucleus. This is just looking again at the ionic radius as a result of those changes in electron configuration. So cations are always smaller than the parent atom, and then anions are always larger than the atoms that they are derived from. This is because of the repulsion for the same core charge versus being held more tightly and losing that shell for the cations. It's also important to remember this term, isoelectronic. These are atoms or ions that share the same electron configuration. Okay, so things that are isoelectronic can have different radii depending on whether or not they are negative ions or positive ions or the neutral atom. This is a summary of the trends, remembering you should have your reference periodic table, and we're going to annotate that periodic table with each of the trends. So the atomic radius increases down a group while it decreases across a period. The ionization energy will decrease down a group while it increases from left to right across a period. The electronegativity decreases down a group and increases across a period, remembering that fluorine is the most electronegative element, and our non-metals will have higher electronegativities than our metals. You should read through these explanations carefully and be able to explain each of the properties that we've seen as a result of the core charge, their electron configuration, and their distance from the nucleus. That's it for physical trends. Next up, we'll be talking about chemical trends.